That doesn't think I have two right here. No, I have two right here. Smaller one.
The smaller.
Okay, that's it.
Okay, it's 10.
You hold the 10 for now, and we're settled, we're even.
We're even for now.
And then we'll sign it.
Okay.
Good morning, welcome to the seminar. Beautiful house here today. We do have a special speaker, and I'm Steve Paul, the chair of the Chemistry, Physics, and Math Department, and I'm here to just welcome you and thank you for coming out. And we've been really excited. We've had a couple of geologists from the Solid Rock Lectures organization. They're a ministry of Christians who are professional geologists, and they have a heart for Christ and a heart for God's people. And just want to give a plug to, we have the founder of Solid Rock Lectures Ministry here today, Dr. Ken Wolgamuth. Yeah. And Gregg Davidson, who will be speaking. He is the chair of geology and geological engineering at Ole Miss. And he'll be talking in just a moment, but I do want to give a little bit of a plug because they've got this beautiful book that's just come out, and it's called The Grand Canyon, Monument to an Ancient Earth, and it is a beautiful, beautiful book with beautiful pictures and everything, and you can get a special price, and you can get it personally signed by these guys here today. So I think it's, what, 25 bucks? They want a copy? So you'll definitely want to get a copy. They are wonderful. And so anyway, just to give a plug and let you know that Ken will be around this afternoon, right? And we'll be going to lunch together if you have time to go to lunch with us and talk further. We invite you to do that afterwards. And also, Ken will be here this afternoon to meet with you individually. He'll be in one of the offices down at the science wing, and if you want to meet with him and discuss it further, I think Greg's going to have to be heading on out to getting home.
After lunch.
Yeah, right after lunch. And so, anyway, if you want to talk with him, come to lunch with us, okay? Good. Now, a little bit about our speaker here today. And Gregg Davidson, he grew up in a family with two preachers, grandfather, and a biology professor, his father. And so he has a BS in geology from Wheaton College and a PhD in hydrogeology from the University of Arizona. And now he's been at Ole Miss. How many years have you been at Ole Miss? 20 years, and this poor guy has been made chair. So give him your condolences.
Your condolences are accepted.
And these guys really, their ministry is going out into different Christian venues, and mostly to speak to Christian groups about how to fit modern geology together with true biblical faith. And so I really appreciate these guys, and give them a warm round of welcome.
Thank you. So to set the stage for what we're going to do in the next 45 minutes, the stuff we're going to be talking about I find very interesting. I am a scientist, so obviously I really enjoy doing science and studying the history of the Earth. I'm also very committed to my Christian faith and to the inspiration and authority of God's Word. If the church was not making a major issue out of questions of age, it would still be an interesting topic. Maybe I would give a talk here or there, but I probably wouldn't be writing books and doing multiple conferences and seminars every year. But because people have made it a divisive issue, then it seems that it becomes more important that we do a little bit more exploration and increase our understanding so that we can better address potentially contentious issues. That said, my mission today is not to, as I said last night, it's not to produce disciples where you all agree to my particular position or I won't speak to you. One of my best friends back in Mississippi, who's the chair of the chemical engineering department, is a pretty staunch six-dayer. He holds to a young earth position. And we get along great because neither one of us makes this particular issue a dividing line between the faithful and unfaithful, between those who honor God's word, the authority of God's word, and those who don't. When we actually talk about this issue, it can get a little warm, but love prevails. All right, so last night the subject was almost exclusively Bible. Today we're going to look almost exclusively at what we find in nature. And I'm going to take a bit of a risk this morning because none of this is scripted, and I'm not actually going to give a presentation per se. What I'm going to do is to very briefly describe a conventional geology, old Earth understanding of Earth history. Briefly describe the young Earth geology version of Earth history, and then invite you all to think about how we might go about testing these different models. And depending on what kind of information or feedback I get from you, I will dive into my PowerPoint slides and see if I can find something that we can pull up to look at what we actually see in nature. So if this turns out to be a dismal flop, you only have to survive 40 minutes max, and you're done. So we'll see how this goes. All right. So the overview. Right, so just have a few text slides. They won't be, most of them won't be quite this boring. Conventional model. Earth history is characterized by both slow and rapid processes. There's a common misunderstanding that within conventional geology, that geologists think that everything in the Earth happens slow and always at the same rates that we see today. That's not even remotely accurate. Geologists today recognize things like violent volcanic eruptions, some much, much more massive than anything we've ever seen in human history. Things like enormous meteorite impacts that have done colossal damage to various places on Earth. So conventional understanding includes both very rapid, violent processes and slow, gradual processes. In fact, one geologist put it this way, that Earth history is a lot like a soldier in war. That most of their experience is long, tedious boredom interjected by moments of sheer terror. Not that geology is boring, by the way. So those catastrophic events are understood to be distributed through time and space, not all happening at the same time. Radiometric dating is believed to yield reliable ages, ranging from basically yesterday to maximum ages on Earth of about 4.5 billion years. That's younger than the universe age, which would be 13.8 billion. So our whole sun and solar system is a relatively newcomer in the galaxy at about 4.5 billion. Plate tectonics. We'll describe this a little bit more in just a second. So we've got solid crust on the surface of the Earth that is actually mobile. It's not stationary. It's thought, and there's evidence that those plates have been moving through most of Earth history. The rate at which they move has varied, but in general, we're talking inches per year. So variations around, down to, say, half an inch per year up to maybe something like 7 inches per year. And that the fossil record represents changing life over vast periods of time. So that's certainly not an all-encompassing description of conventional geology, but it's some of the things that we'll consider this morning. Just a few illustrative slides. So when we're talking about the formation of Earth's layers, within the sedimentary record, the most common way we see this is, say, along the coastline, where you have rivers that are discharging sediment, and you may have sands coming out near the beach. Finer particles travel farther out and begin to settle out. And if you have something like sea level rise, so we're keeping track of this little box here, which is repeated here, as the sea level rises, now, because we're in deeper water, the sand is getting deposited up here, and the finer particles out here, so you start to get layering, where you may have one sand layer and one clay layer. Sea level rises some more, and we may have limestone, reefs, for example, carbonates that begin to form in still deeper water. So we have these kinds of processes at work. What causes oceans to rise and fall? Well, we can have things like climate change, which is actually not a new thing. The Earth's history has been filled with climate change, which is not to say that we're not contributing to it now. But temperatures have been much more warmer and much colder in the past. If you start piling up water into continental glaciers, that's coming out of the oceans, ocean level is going to drop. We also have plate tectonics. And how many people heard Dr. Wildermuth's talk like an hour ago? Okay, just a few of you. So for the vast majority of you, you've not seen this. All right, so the idea of plate tectonics is, so I'm going to back up here, this is not just speculative. There's a ton of investigations that go on looking at rock types and matching up rocks where we see at the edge of one continent and another that suggest that in various times in our history, all of the continents have, or most of the continents have been at one spot at the same time. This is an animation where we're going back some millions of years, where we've got, some of you heard of like the continent Pangaea, so this would be representing that early continent. And what it's showing here is these would not have actually been outlined back then like they are shown in this, but this is to help us keep track of where is Africa, where was South America, North America, etc. So we're just going to let this run. And there's one cool thing right here. If you watch India, we kind of need sound effects here, right? All right, so if I go back, and I'm just going to repeat that last bit here. We're going to fast forward to here. Okay, do you all know what's sitting right there? The Himalayan mountains. There is a reason why they are as tall as they are and why they're still growing. India is still moving northward into the Eurasian plate. So if I now go and look at this again, so this would be an illustration of this process just in 3 frames, where here's the Indian continent, it's headed towards Eurasia, the oceanic crust is what we say is subducting, it's actually thinner, weaker crust, which dives underneath. Sediments that may be accumulating here end up getting pinched and pushed up on top of those mountains, so that we have a mechanism for how we could get, say, fossilized rock, a rock with marine fossils, up on top of Mount Everest. Okay, all of this gives rise to what we refer to as the geologic column. And early in geology history, there was never a claim that we could find the geologic column all in one place. There was a process of relative dating where they would find pieces of layers of rock, they'd go to somewhere else, they'd find where there was overlap, and they could kind of put these puzzle pieces together to get this overall geologic column. Since that time, however, there's like 26 places around the world where you can drill, people have drilled, and encountered every single one of these geologic periods in this order. So you can, in fact, find the entire geologic column represented in one place, about 26 places around the world. Okay, so most of these names are just based on places where most of the study was done. So like the Jurassic period, the initial studies were done in the Jura Mountains, so it got named the Jurassic. And that was also partly because when they were doing this originally, they had no idea how old they were. They could figure out the order, but they didn't know exactly what the age was. Ages didn't come along until later, when radioactivity was discovered, and they figured out ways of using that in order to figure out ages of these layers. So we're looking at ages here in millions of years. So we're getting back between the Cenozoic, Mesozoic, and Paleozoic. We're looking at on the order of 600 million years. And then older rocks down here. All right, we're going to contrast that with the young Earth flood geology understanding. So in the flood model, the majority of the Earth's layers were characterized by a single massive catastrophic flood. Radiometric ages are considered to be unreliable. Plate tectonics was very fast, initiated during the beginning of the flood, where it's argued that subterranean water, pressurized, broke through the crust, rapidly thrust plates apart up to 40 miles an hour, building up mountains and creating ocean trenches in a matter of days. Ruptured crust released the subterranean water. This process is also said to have initiated mega tsunamis, where they would have swept entirely across continents, ocean to ocean, destroying all life in its path. Thus, the majority of fossils that we find in the Earth's layers were buried by that one-year flood. There is an allowance that between Adam and Noah, there could have been some death and preservation, but the vast majority of the Earth's sedimentary layers that contain fossils would be flood deposits. Now, interestingly, just my little depiction of the massive tsunami about to sweep up on the coast. A couple quotes are relevant here. Henry Morris was kind of the founding father of the modern flood geology movement. Said that creationists do not question the general validity of the geologic column, at least as an indicator of the usual order of deposition of fossils. So there's not a lot of, or there's a general acceptance of the order that conventional geologists say exists. However, the arrangement of the fossils in there, Scott Hughes has this quote that the young Earth creationists maintain that such fossil zonation, where we have an apparent order in the fossil record from simple to complex, that reflects combined effects of hydraulic, ecological, and physiologic sorting in conjunction with the Genesis flood. In other words, they're all swept across, but because of differences in density and size and the rate of water movement, that you get this sorting of organisms into these deposits that just give the appearance of there being some sort of progression. All right, so I won't say they completely accept this, but by and large, but definitely not these, right? So what most of them now argue is that these rocks down here in the Precambrian represent Creation Week, a very thin zone of Creation Week to the flood, and then we're breaking the Paleozoic and Mesozoic layers into early flood, which that represents almost the entire Grand Canyon sequence. And then late flood on top of that, and then the Cenozoic, these would all be post-flood deposits, where the Earth is still said to be experiencing some violent perturbations, which is why we have some catastrophes that come after the flood that may bury creatures, residual volcanism, things like that. All right, so those are our two models. So we've got 35 minutes now. So we're not going to be able, obviously, to do any kind of exhaustive testing of models. We may end up only doing 3 or 4, we'll see. So here's where the experiment begins. And I want to get your input for how would we go about testing these models with what we find in nature. And if you need a little help, we might refine this. You're welcome to pick any topic. But let's just say we focus on the tsunamis sweeping across the continents versus conventional view that no, this has happened over a long period of time, rising and falling oceans, mountains eroding, sediment filling in the valleys, burying organisms. What would we look for in nature to try to put those two models to the test? Yes?
Would there be examples of marine life?
Examples of marine life in the middle of the continents. That's excellent. So one of the things we have to do is think through complications to our test, right? One of the things that I didn't mention with the conventional geology model is that with continents bumping into each other, we can have pretty substantial rise and fall of the continents themselves. So there's an extended period of time where the whole central portion of the North American continent was under sea level. So there's this big seaway that cuts right up through the continent, but still with this very orderly, according to conventional geology, this very orderly sequence of fossils within that. So with that additional information, we can't just look for marine fossils on the continent. But it was a great idea. I liked it. I like the way you're thinking.
Did you look for fossils that spread between the layers?
Elaborate. What do you mean?
Well, if you have a fossil that spreads between 3 different layers, you know that that didn't happen slowly. It was rapid.
You mean like a single fossil?
Yeah.
Okay. So, yeah, if you find, at various times there have been arguments that you can find, like, say, standing trees that go through several layers. Or at one time there was a whale that was found in a layer sitting at a 45-degree angle. It's like, how in the world could it? That had to be really, really fast, right? Well, in the case of the whale, they eventually realized that the layers were sloped. So it was originally flat, the layers were tilted. With something like the trees, it's very possible. If you remember that in the conventional geology understanding, that includes some catastrophic processes. So you could have multiple layers deposited in rapid sequence in a particular location that would do that. But we're heading in the right direction. And by the way, that explanation, it's another example of, if we find that, it's not speaking conclusively for either model, right? So we're kind of fleshing out what are the kinds of things that we need to be thinking through in order to find some way of actually determining which model is best supported by what we find in nature. So what else? Yes?
Evidence of intense water damage, maybe?
Evidence of intense water damage. Perhaps. So we have, what are you thinking of?
I don't know, I just know that if a tsunami happened and there's lots of water everywhere, then
Okay.
normally like,
So not like just getting soaked, but the idea of being tumbled and into a chaotic mess.
yeah. And
Okay. All right, I think we can do something with this. If we've got a giant tsunami hurtling across the continent, and then finally the waters settle out, we're going to expect that we have, as perhaps the norm, fossils that look like they're in a jumbled mess. And what kind of mixture do I expect to see of organisms?
All sorts.
All sorts. So marine, terrestrial. And I think it's important to remind ourselves that we would expect that as the norm, right? So if we just find one place by itself that seems to have that, it doesn't really speak strongly to either model, because the conventional model also has periodic catastrophic events, right? And I can even have things like, if I have a gully washer in a valley that's next to the ocean, and land creatures get swept into the valley and carried out to sea and settle out, I'd fully expect to find some places where I have a mixture of terrestrial and marine. So really the issue becomes, is it the norm, or do I have it in just isolated places? Okay, so we are ready with that then. And I did not plan this, but it's like the next slide. So here is Japan just before, well, I won't say just before the big tsunami hit in 2011. This is a tsunami wall. It was built specifically to hold back tsunami waves if they were to come into this bay. Big earthquake occurred off the coast of Japan, and it's not just an earthquake that causes a tsunami, that there was a shift in one of those tectonic plates, where the sudden shift caused the ocean to suddenly, I don't remember if it's rise or fall, but it then sets up this giant wave that heads inland, and as it heads inland, the front end of the wave slows, the back end catches up, it gets higher, and this is a picture of that same place with the first tsunami wave pouring over that wall. Now, this looks nothing like a tsunami that would cover an entire continent, right? This is tiny. And yet it's still utterly devastating to this coastline. The aftermath of that, now this is not actually the aftermath. This was just an empty lot that was before the tsunami. This is what it looked like afterwards. This gives a really good example of what we would expect to see, right? We've got marine and terrestrial in the same layers. All right. So we want to find out what we see in nature. Now, I'm going to skip ahead here, and we're going to look at some interesting quotes. All right, so these are two Young Earth quotes. Carl Wieland makes this statement: sea, land, and lake creatures have been found buried together in one massive fossil deposit. Can evolutionists or creationists offer the most satisfactory explanation for what happened? Seems to be arguing that the norm is this great mixture. Andrew Snelling, notice that many of these examples of how marine and land-dwelling creatures are found buried together, and how this could have happened unless the ocean waters rose up and swept over the continents in a global catastrophic flood. Now, let me ask you this. This is a slice of a layer cake. Would you say that this layer cake has frosting and cake mixed together?
Yes.
Oh, I heard yes. Oh, wait. What? Why? Oh, wait.
Because I didn't know if you meant like mixed as in like they're together on the same cake, or mixed as in like actually.
Exactly. If I just say, I've got a mix of cake and frosting in the same unit, that's technically an accurate statement. But I have to follow up with that, like, what do you really mean by that? If you mean that it is a jumbled mess, it should look like that. All right? When I go into a place like the Grand Canyon, you can indeed find layers or units. We talk about formations as being a particular sequence of rock. And you can find marine and terrestrial organisms in that same formation, true enough. So if I go to, say, this little formation right here, it's called the Temple Butte Formation. it has terrestrial and marine fossils in it. However, it just so happens that they are exclusively terrestrial in the bottom and exclusively marine in the top. They are not mixed or jumbled together. And when we look all over the world, that is the norm. Oceans rise, oceans fall, we get terrestrial organisms, we get marine organisms. There are very, very few that actually have mixed organisms in them. Yes?
So, I'm actually traditionally a young earth creationist, but this thought just occurred to me. If a massive wave swept across the continent, and so you have, all these animals, wouldn't all of the fossils be like evenly distributed over the area? Like you wouldn't have concentrated areas, would you?
When you go to the aftermath of one of these normal-sized tsunamis, they're very chaotic. You're not necessarily, like, we don't see another one of these ships in this image, right? So we have a pretty spotty distribution. It's not laminar flow, right? You have very turbulent flow. So things get mixed up and you end up with concentration, especially if you have something like an eddy that forms, right? You end up with a concentration of things in that eddy that you don't see where the water's ripping through in a channel. All right, now, this is by no means, is this example considered, and I wouldn't consider this definitive, right? This is one example of a lot of different things we could look at. But it's illustrating the idea that this is not just a matter of what position do I choose to take? Which one do I think is more honoring to Scripture? Because you can make really good arguments either way. There are things we can actually look at in nature to compare these models. So what else might we look at? Yes, back.
Well, that example also is where it came in and then it came back out.
Right.
It didn't sweep all the way across the island from one side to the other. I mean,
True.
you would have boats, but the houses and everything else would be washed off the other side. It wouldn't have, when a tidal wave goes in and then it comes back out, it's drawing everything out that was back out. But if it totally goes over it, it's just going to wash away whatever was on top.
Okay, that's an interesting observation. The dynamics of the outflow are not the same as the inflow. The outflow tends to be lower energy, more distributed. So it's not, you don't, in fact, well, if you did get everything that was washed in gets washed out, which is actually not what you were saying. You said if it goes all the way over the continent.
Yes, because
Yeah, but we're still, with that kind of energy, there are things that are going to be carried across the continent and dumped out to sea. So when we look at those sediments that were dumped out at sea later on, we should find the chaotic mixtures of the ocean creatures that got pulled up onto the continent, tumbled with the marines, with a terrestrial, and dumped out the other side, with a bunch of stuff that was trailing behind and left there. So we should still see, as the norm, mixtures. And maybe in some places on the continent we wouldn't see very much. Maybe most of it would be out there in the marine sediments. But either way, we should still expect to get this chaotic mixture. And we're not seeing that. What else can we look at?
One of the questions I would have about the conventional view is you had a slide that had a picture of the several layers and it had the dates that go with it. And on the bottom layer is a certain kind of crab that was, I think, said to be extinct for a very long period of time, but then we later on found it. In fact, I've seen one in the Florida Keys. But we placed this crab at about, I think it was like 2.3 billion years ago. But if this was one of the first organisms to have evolved, we also find that it has one of the most complex eye sites of different organisms. So how could that have been in the bottom layer, and why does that make sense for it to have been one of the original organisms if it is extremely complex? Like, compared to human eyes, it's more,
Right, yeah, so good question. what I want to do, I both want to answer the question and keep us on topic. So we're looking for ways of testing models as opposed to addressing potential challenges to a model. But so I'm kind of going to give you an overly brief answer.
One of the testing of it.
Oh, okay. Actually, we can do that. So if I rephrase that a little bit, it's that in the conventional model, when we're looking at these layers, if we say that life has changed over time, then we should never find a complex organism in the very oldest sediments. And we should have a pretty consistent ordering, whereas in the flood geology model, we should expect a lot of places where we've got really complex organisms in multiple places and a much more random distribution. Is that fair?
Yes.
Okay. All right.
Can you also define complex?
Yeah, define complex. So I think, so when you're mentioning a crab, I think you were conflating two different things. A crab, it's a little genuinely a crab that was thought to have gone extinct, and they found living versions of it. That's called a Lazarus species, something we thought went extinct, and there it is. The complex eye thing, I think you're talking about trilobites.
Yes.
And trilobites are found in really old layers. You go back more than 500 million years, and you're finding these creatures that have a pretty complex eye structure. So there is, in fact, some biological complexity in really old layers. If you look at that in context of all the layers, though, you go before those into older ones, and you are, in fact, getting simpler and simpler organisms in the Precambrian. And as you move forward, you are getting a greater diversification of life, and you're starting to get into things like internal skeletons and the ability to live on land and many, many adaptations like this. But we want to not just hear me talk, we want to look and see what we actually find out in nature. All right, so I'm not going to have slides that exactly speak to that, but here's one. So in that, this would just be talking a little bit more about what I would expect in the flood model. That some creatures, when they are killed, especially in a flood, bloat and float. And we've got examples here of a fish, a cow, and a lizard. So we've got reptiles, mammals, and fish. We would fully expect that after a process like this, we would get some layers that have all of those in them. That have reptiles, that have mammals, that have fish, all mixed together. We would also expect, oh, how about these? All right, these are, and this isn't exactly addressing your question, but it's getting at the same idea. These are marine reptiles that were air-breathing marine predators. Some of them were fairly small, some of them were huge. Some of these are very, very large. They would have filled the same kind of niches as these. Right? These are marine mammals, where we have seals, we have killer whales, sperm whales, manatees, all of them except the manatee being marine predators. So they're swimming over the whole ocean, likely eating the same kinds of food. If any creatures ought to be mixed in a global catastrophic flood, it would be the marine reptiles and the marine mammals. All right, so here is the flood model. Here is where we find all of those marine reptiles. there's where we find all of the marine mammals. There's no mixing at all. Okay, these are flowering plants. According to conventional geological understanding, flowering plants didn't come on the scene until quite late in the Earth history. So we would expect to only see flowering plants in the upper layers, the younger layers, none in the lower layers. It gets better than that, though, because this is an example of flowering plant pollen. So this is tiny, tiny stuff, electron scanning microscope image. You can get an idea of why they cause allergies. It makes me not want to go outside when I see this kind of a picture. These things get released into the air where it doesn't take much of a breeze to carry them great distances. You imagine this now being swept up in a global catastrophic flood. And we should find this pollen everywhere. So this makes for a pretty good test, I think. All right, so flowering plants and pollen, we find only in these layers. None in these. If we go to the Grand Canyon, I mentioned that the Grand Canyon, these only represent what we call the Paleozoic layers, so they're fairly old. If you travel over to like Bryce Canyon and Zion, you're getting into, at the surface, some of the younger layers. You get over to Bryce, you're getting into younger layers still. And there's holes that have been drilled to verify that these continue like they're shown here. So like there's a, that's the topmost Grand Canyon layer that can be found underneath the surface over here. This represents kind of an illustration of the kinds of organisms that we find in these different layers. So yes, by the time we get just into here, we've got some fairly complex organisms, but nothing that can live on land yet, nothing that has an internal skeleton, nothing that has we don't have things like even jaws on these fish. We don't see jaws on the fish until up here. And so there's this apparent increasing in complexity and diversification of life. When I'm looking at the Grand Canyon, these are the only kinds of organisms we see in the entire Grand Canyon sequence. The ones that are above there, we only find in these layers. So in all of that exposed rock, a mile thick, you want to hazard a guess how many birds, flowering plants, pollen, mammals, or marine reptiles we find? Zero. Oh. Good point. As a matter of fact, birds are capable of flying down into the canyon and sitting on a rock. So technically, yes, we do find those down there. Not dinosaurs. When we're looking at the rock layers themselves and what they contain, no bird fossils, no mammal fossils, no flowering plants, no marine reptiles. Yes?
As you have a layer of sediment or any kind of rock layer exposed for really any length of time, you start to see weathering effects through wind or water.
Yes.
And as the next layer is going to put onto that, you're going to see a merge effect. So
potentially.
When a hurricane would come through, you would see a new layer of sand put over and you can see a distinct layer. As time passes, water and similar methods, including animals, often blend them. So you would often expect to see quite a bit of layer blending where you have a transition zone. However, when you go to a place like out west very often and you look at exposed layers of rocks, you often find very distinct, you have one layer and then suddenly within an inch you've got another layer.
Yeah, and you can actually end up with that with either conventional or a flood geology model. So by itself, it's not very distinguishing. But just to elaborate briefly on how that happens, there's a variety of mechanisms. One is if you've already got sediments that have hardened into rock, and now let's say that the ocean level falls, and you begin to erode that down, so it's now eroding into fresh rock, you get ocean level rise, and you get deposition starting to happen on top of that. And when that turns to rock, you now have a very sharp line between the two. That could potentially happen in either flood geology or the conventional model. Within active depositional systems, that transition may come from a result of, let's say that we've got clays accumulating, and the water level falls, so that we have sand now being delivered on top of that. Well, all the critters that lived in the mud don't like sand very well. So there's not much of a time of living in the sand and bioturbating that transition. So you can end up with a pretty sharp transition that way too. And that also could happen in a flood model or a conventional model. So it's interesting, but it's not very definitive. Yes.
Okay,
and I think we've got 4 minutes. All right.
So I don't know if this is kind of on topic.
4 minutes.
But at the same time, I don't know.
Okay, go ahead.
So say in a flood, there's going to be a massive, large amount of water on top of the animals for a short period of time while they are absorbing water. Do you think that this pressure could possibly, from this water, because the lower you get, the more pressure there is on it, do you think that pressure could possibly push it down into the sand maybe, and the sand would hold it down?
Yeah, so the question was, if you've got a massive amount of water, could the water pressure push things down into the sediment? It's a good question. With water pressure, it is unidirectional. Right? So if you swim to the bottom of the pool, you don't suddenly feel your body being pushed lower. You feel the pressure from all directions. So the effect of a massive amount of water would just be compression of the organism, not pushing it in a particular direction. And I think we could probably so we don't have enough time to look at maybe another method of testing the models, but I can take another question before we dismiss. Boy, I think you have your hand up first.
So I was wondering about the soft tissues that have been found in dinosaur fossils and things like that. How would that work into?
Excellent question. Let's pose a prayer. Yeah, so Mary Schweitzer is a paleontologist from the University of North Carolina. An amazing woman. She's the one who first discovered soft tissues surviving inside the bones of T-Rex. The backstory to that doesn't get told very often is she went to get a PhD as a young Earth creationist, wanting to get an education in paleontology to be able to prove those godless scientists wrong, kind of her words. She still has a very vibrant faith, Christian faith, and she's now a leading advocate of the evolutionary transition from dinosaurs to birds. That by itself speaks fairly loudly. Not conclusively, but speaks loudly. No one ever thought to look inside. I mean, you find a T-Rex skeleton, what's the first thought? Oh, let's bust up the fossil bones. It's like, are you kidding me? It's like, these things are precious. She was one of the first ones that actually looked inside these things. And she took a huge amount of flack, including from the scientific community. So, is there bias within science? Yes. Don't even get started on that. So she, for a long time, took a huge amount of flack. because honestly, some of them were just stuck in the mud where they thought that they understood things better than they did. There were some that were actually concerned about giving fuel to the Young Earth movement, which it has given fuel to the Young Earth movement. But nobody had paid attention to just how well a massive femur on the inside could actually protect it from the surrounding environment. And organic tissue is not like radioactive isotopes that decay at a set rate, right? The rate of biological decay depends entirely on its environment. So within that environment, she's made some absolutely amazing discoveries of things that have been preserved. Now, she hasn't been able to find things like DNA. That seems to be too broken down. But she's found things like what look like surviving blood tissues, blood vessels, maybe blood cells in them, but not yet confirmed. All right.
It's time. Let's thank our speaker. You're welcome to join us in the Joyce Room for lunch. And welcome also to
Just a second. I have a geologic timescale card here that's on the corners of the table. If you walk out, feel free to get one. On this side, there's one paper you can take for free. We're not here to sell books, but here.
Oh, I'm in my chair over there.
Only one of them found their way to me.
The pile over there, where I was sitting.
Over there somewhere.